Alright everyone, welcome to the final unit before you guys take the AP exam. In preparation for the AP exam, we're going to start pulling together a lot of material from first semester. So for a little warm-up, what I'm going to have you do with the first portion of these notes is to describe the motion of a particle. In this case, we've got a bee, and this bee is making a trip from the hive to the flower. Assume that a positive velocity indicates a direction towards the flower, and the velocity of the bee is plotted below. So we've got velocity on the y-axis, and we've got time in minutes on the x-axis. So I'm going to have you describe the motion of this bee. When is it traveling towards the flower? When is it traveling away from the flower? And when is it stopped? So I want you to write that in this section right here, and press pause right now and come on back. Alright, so I'm going to put up the solution here. How'd you do? We've got the bee is traveling towards the flower from 0 to 2 minutes, and he's moving away from 4 minutes all the way until 8 minutes, and then he's stopped when his velocity is 0. Okay, so if you have any questions on this, this was back in section 3.4 all the way back then. So if you have any questions, go ahead and reference your notes from then. Now what I'd like you to do is sketch on the exact same graph right here. I want you to sketch the speed of the bee. All right, come on back. All right, so speed is talking about the absolute value of velocity. So when velocity is positive, the speed is the same as the velocity. And we get to this point, no big deal. And now here's where it's going to be a little bit different. Instead of going to the negative, we're just going to draw the absolute value of that. Come on back, and like that. So that would be the speed. Wow, that looks like a third grader drew it. Awesome. All right, now we're going to answer some questions, but before we do that, I'm going to have you go even further back into 3.4, and I'm going to have you describe when the particle is speeding up and when it is slowing down, and justify it with a sentence. And 3, 2, 1. All right, so my solution, my explanation are shown right here. The biggest piece to justifying any answer in this is making the connection between the bee's velocity, which is plotted, and the bee's acceleration, which is going to be the slope of the velocity. This sentence right here is the justification for everything I'm about to say. The speed is increasing from 4 until 6 because the velocity and the acceleration are both negative. So velocity is shown here from 4 to 6, it's negative, and it also has a negative slope. The bee's velocity is speed is decreasing from 0 to 2 and from 6 to 8. So from 0 to 2, the velocity is positive, it's above the axis. However, its acceleration, the slope, is negative. And then again from 6 to 8, here the velocity is negative, it's below the axis, but the acceleration, its slope, is positive. So remember, anytime you have opposite signs, you've got a speed that is decreasing, or you could say slowing down as well. Okay, so there's our summary from first semester, section 3.4. Now we're going to move on and talk about the new material. Okay, so first semester was connecting slope, second semester is dealing with area under a curve. So the first question here is, how far has the bee traveled? Okay, well remember that a positive velocity is indicating a direction that is towards the flower. Remember, direction is indicated by velocity. So we're going to go ahead and recognize that the top half of this thing right here, this is all when the bee is moving towards the flower. Okay, and then this bottom region over here, this would be considered the direction away from the flower, or the time that the bee is moving away from the flower. So far, how far has the bee traveled? You just want to know overall distance. You don't really care about the direction for this thing. And we would expect a unit of feet for this problem. So if you're starting off with a unit of feet per minute on the y-axis and minute on the x-axis, the only way to get those minutes in each of them to cancel is to multiply, and that's what happens when you find the area. So this region right here, since it's a lovely little triangle, you can do 1/2 Okay, the base distance is 2 minutes, and the height of this is 100. Okay, so we're getting 100 feet for that top region. Okay, for the bottom region here, 1/2, our base this time is 4 minutes, and our height this time is -100. And you'll see how that comes into play in just a second. So this time we've got -200 feet. Now, how far has the bee traveled? Well, if he's moving 100 feet towards the flower, and then he moves 200 feet away from the flower, he's still traveling a total of 300 feet. Okay? We're not curious about which direction he's moving. We're talking about if you're running downstairs for the 12-minute mile, even though you're going in circles, you are still traveling a distance. The question that might be a little bit confusing for some people is displaced. How far has the bee been displaced? Well, if you travel 100 feet towards the flower and then you move 200 feet away from the flower, you're actually 100 feet further back from where you started. So -100 feet would be the displacement. Okay, so again, for that one, we took the 100 feet and we just added the -200 feet. Okay, so that's where the -100 comes from. All right. All right, so just recapping here. If x of t is a position of a particle at any time, then x prime of t is our v of t, which is our velocity. Okay, and then x double prime of t, and then x double prime of t is v of t's derivative, which is a of t, the acceleration. Okay, so if we work backwards then, and we take the antiderivative, or the indefinite integral of a of t, we're going to have v of t. But here's a little difference. Tack on that constant. And then the antiderivative of velocity is going to be the position plus that constant. And remember, total displacement, this is going back to first semester, final position minus the initial position. So if we're talking about a region from x equals a until x equals b, closed interval, the displacement will be x of b minus x of a. It would also be the antiderivative, or I'm sorry, the definite integral of the velocity over that exact same time. So this is where we're starting to link first and second semester material together. All right, total distance traveled takes into account any change in direction. Okay, so if we're talking about distance traveled, or the total distance, you need to make sure that we're basically talking about a speed graph. And to do that, you would have to take the absolute value of the velocity and then integrate it. Okay, so that's the definite integral from the interval from a to b of the speed of v of t. Please note, this does not equal if you just find the definite integral and then you make it positive. They're not the same thing, and I point that out because enough students do that now I finally had to put it in my notes. Okay, so they're not the same thing. I don't want you to do the second one. Okay, so I'm actually going to well, I can't delete that whole thing. So we're just going to erase that second part. Or actually, I'm going to put a big red X through it. Right? Red is Deerfield. We don't like it. Okay, so don't do that one. Okay. If we are asked to find the distance without the aid of a calculator, all you would have to do is locate the x-intercepts, or the time intercepts, or the zeros of the graph. Okay, so the zeros of the graph, remember this is a v of t graph, and break the graph into intervals so that you can identify where the velocity, if you take the absolute value, is actually going to change the graph or where it wouldn't change the graph. We'll do more examples of these in class, so if you're like, I don't get it, hang with me, it's all good. All right, so our first example is we've got a velocity of a particle moving along an axis, and don't be thrown off. The horizontal axis is just identifying to us that this is not going to be going in circles or any kind of two-dimensional motion. We're just talking about one direction, okay? So it's given by the equation v of t equals 0.5, the quantity t minus 2 cubed minus 2t plus 1, and it's over the interval from 0 to 5. So the first thing I want you to do is to locate some important time values here. So this is our time, this is our v of t. We're starting at 0, we're going all the way until time equals 5. Okay, there are going to probably be some important factors here. To describe the motion of the particle, you want to talk about where v of t is greater than 0. You want to talk about where v of t is less than 0. I want you to talk about where the particle is going to be speeding up and slowing down, so you'll need to know about a of t as well. And you'll need to know where a of t is less than 0. All those things paired together is going to help us identify the motion of the particle. So to do that, because we have a calculator with this thing, v of t greater than 0, well, that is talking about this region right in here. Okay, so the first thing that I'm going to do is I'm going to break this graph up into some parts so it's a little bit easier to talk about. From 0 all the way until that point right there, we're going to have a negative velocity. It's below the axis. So I'm going to underline that with the purple. For the v of t greater than 0, we've got the orange part of the graph. For a of t greater than 0, we're talking about a positive slope on this graph. So we're talking about from here to about there, and we're talking from here for the rest of the time. So that's a of t greater than 0. And then for a of t less than 0, we are talking about a negative slope on the velocity graph. So we're going to do that guy in yellow. Okay, so we've got a lot of different colors going on in here. So what I'm going to do is identify the fact that we've got some important parts on this graph we need to talk about. And I don't like to carry out all the decimal times every time or the decimal points every single time I write these time values. So I'm going to identify this time value as A, and we'll identify this time value as B, and we'll identify this guy as C. Okay, so the important time values that we've got going on, we've got A is a 0, or I'm sorry, A is a maximum of the velocity graph, B is a minimum of the velocity graph, and C is going to be a 0 of the velocity graph. And since this is a calculator OK problem, go ahead and use your calculators to identify those time values right now and then come on back. Okay, so for this particular graph, these are the values of interest to us. Notice that I carried the decimal point all the way out, and I represented it with letters A, B, and C. You can use these in your solutions now. Additionally, if there's work that you have to do with them, which there will be, you can store these values on your calculator. And if you're not sure how to do that, make a note in the margin right now and make sure you ask me in class tomorrow. being able to store values and use them on your home screen is going to be incredibly powerful for you so that you don't have to worry about rounding errors. Okay, so when we go back to describe the motion of the particle, again, we are talking about this particle, since it's moving along a horizontal axis, we're talking about motion to the left and to the right. So for v of t greater than 0, we're going to say this would be moving right. And this would be moving left for v of t less than 0. And on the AP exam, you'll have lots of room to write all this stuff out, so don't abbreviate things like I'm trying to do right there. Okay, so moving to the right, v of t greater than 0. So the only time that that happens is for that orange part of the graph, which we identified from C until 5. And because I indicated what C was equal to, this is completely legitimate. Okay, moving to the left is that velocity is less than 0, so that is the entire time from 0 until C. And this could be a bracket. There we go. All right. For the particles speeding up and slowing down, we have to talk about A of t and v of t having the same signs. So, but the first thing that we're going to do is identify where A of t is greater than 0. And remember, that was two regions, brackets here, from 0 until A, and again from B until 5. Okay, so A of t less than 0 was from A until B. All right, so you can say that the particle is moving to the right from C until 5, moving left from 0 until C. You can now say that the particle is stopped at t equals C. For speeding up, okay, for speeding up, remember you have to have v of t and A of t have to have the same signs. All right, and we need to make a statement in here because we don't have any information, visual, verbal, or otherwise, talking about A of t. Just make a statement in here that A of t is the slope of the v of t graph. Okay, so now we can make all those statements. So this particle is speeding up anytime they have the same sign. Well, from time equals 0 until time equals a, we've got a negative velocity because it's below the axis, but a positive acceleration. So that's actually slowing down. So we can write that over here, slowing down. We've got A of t and V of t have opposite sign. So that was from 0 until A. From A until B, we have negative velocity and negative acceleration, so that works from A to B. From B until C, we have negative velocity but positive acceleration, so we're slowing down again. And then from C until 5, we've got positive velocity, positive acceleration, so that is from C until 5. Okay, I think that covers the motion of the particle, and now we can move on to B. For this one, it's asking us for the displacement of the particle over the interval from 0 till 5. So displacement is the final position, which would be x of 5, minus the initial position, which is x of 0. Try that again, x of 0. Well, I don't have any information about the x graph, about the position graph, so I'm going to utilize the information that we wrote down on the previous page, and that is that you can find the velocity, you can do the definite integral of the velocity from 0 until 5 of v of t dt. So just do that region, or that part right there, on your calculator on your home screen. And again, you've got the calculator for this. So you should be able to get an exact answer. You don't have to do any integrating on your own. Your calculator can do all the work for you. That's why it's on the calculator portion. And when you do that, you should get an answer of negative 11.875, 3 decimal places for all final answers. And don't forget units here. And since I am looking back here, I didn't give you any units, so you could just write units, or you don't have to write anything at all. I'm going to just put units in here because I'm reminding myself that for some problems I will have them. For the last one, what is the total distance traveled over for the particle over that interval? All you need to do for this guy, total distance, is asking you to do the definite integral over a time interval, but this time of the absolute value of v of t dt. So on your calculators, just make sure that you put absolute values around the function first and then integrate. And if you do that, you should get an answer of 13.864. Okay? And again, units. So the idea here is to pull everything together and just utilizing the definite integrals to find us displacement and distance traveled. And there's a problem on the next page I'd like you to fill out and complete on your own. And I'll see you guys next time.